Good day everyone, my name is Mr. Ademujimi Adedotun. Okay, what we're looking at is what I call equilibrium. What we mean by equilibrium? The body is said to be in equilibrium when the net forces equals to 0. That is, when the net forces acting on the body is equals to 0. Then such body is said to be in equilibrium when we have the net forces to be equal to 0. Let's say for example that we have a box and we have two forces acting towards this direction. That will be F1 in this direction. We have another force called what? F2. Okay, making two forces. And there is what? Another force here called what? F3. Okay? Acting in what? In opposite direction. In opposite direction, opposing or balancing the what? The two forces. In the what? The net force, that is, if what? F1 plus F2 plus F3 equals to 0. It means that the body is in what? Equilibrium. So we can simply say that what? If F net equals to 0, this is what we mean by what? By equilibrium. When the net forces equals what? To 0, that we are having the net force, that is the sum of the forces equals to 0, that will give us what? Equilibrium. That is equilibrium. So we can simply say that what? In equilibrium, net force, that is NF, equals to 0. Equals what? Equals to 0. Equals to 0. So when net force equals what? Equals to 0, meaning that what? Such force is in what? Equilibrium. Okay? In some textbooks we simply say that what? When the sum of the what? Forces acting on the body equals to 0. Okay? When the sum of the forces acting on such body equals to what? The 0, such body is said to be in equilibrium. Okay? Or when the net force, net means sum. Okay? Net or sum equals to 0. Meaning that this is it, right? So let's move further to, that's the first condition. That's the first condition. The number one condition for a body to be what? In equilibrium. Meaning that the net force must be equal to 0. That's the first condition. So let's quickly look at types of equilibrium. Types of what? Of equilibrium. The types of equilibrium. Okay? Before giving us the types of equilibrium, I would like to give us this graph. The graph of potential energy against what? Against X. That will be potential energy against what? Against X. Against X, okay? This will be U. That's potential energy. U is used to what? To denote potential energy. While this is X, okay? This against this. So this is the graph and this is the origin of the graph, okay? Where Y has this and the X has this means. That will be the origin. So we can have it this way. See that? Alright. From this graph, I can deduce the types of what? Of equilibrium to us. The types of equilibrium. Here is what? The minimum. This is the minimum point. The minimum point. The minimum point, that is minimum. That is the minimum point. Why this is what? The maximum. The maximum point. Okay, this is constant. This is constant, okay? From there, what can we deduce from there? We can say the minimum point is what? Is stable. That is stable equilibrium. This is unstable. Unstable equilibrium. Why this is what? Neutral equilibrium. Neutral equilibrium. This is stable. This is unstable. Unstable equilibrium. Why this is what? Neutral equilibrium. Neutral equilibrium. So other types of equilibrium now. Other types of equilibrium. Types of equilibrium. Okay. So we have what? We have one. We have the minimum point. That's stable. That's stable. Stable equilibrium. So the second part is what? Is unstable equilibrium. That is at the maximum point. That is unstable state. unstable equilibrium. Okay? The last one is what? Neutral equilibrium. Okay? So let's look at what is stable and unstable and neutral equilibrium. Stable and unstable, stable, unstable, and neutral equilibrium. When you have this, and this is the what? The ground. This is what we call ground. That's ground. Okay? There's a ball or an object is kept in the what? The big one circle. Okay? We have an object here kept inside the shaded object. Okay? When this object is what? Slightly what? Displayed. Slightly what? Displayed toward the side or toward the side. It returns to what? To return back to his what? His initial position or the normal position. So such object or such body is said to be what? Stable equilibrium. That's stable equilibrium. Stable equilibrium. That is, if when slightly display tends to come to its what? Initial or normal position. So such body is said to be what? In a stable equilibrium. Just slight what? Display. Slight display. So it will just move towards the side, back to the position, or you move it what? Backward, release it. Then to relax and what? The center. That is stable what? Stable equilibrium. Examples are when you have what? Cone sitting on its what? Sitting on its circular base. That's the first example. A cone sitting on its what? Circular base. So this is what my cone sitting on its what? Circular base. Alright. This is what we call the vertex of the cone. Sitting on its what? Circular base. That's the first example. Or we have what? Two. A ball put in a what? Bowl. Number two. The second example. Put in a what? A bowl. Okay? So when we have something like this, let me draw very well. Something like this, okay? Then we have a ball inside, okay? When this ball is what? Slightly, just gently displayed, okay? Gently or slightly displayed. You can see? Slightly displayed. It will move it towards the side, then to tend to what? To rest. To what? In its normal what? Position or initial what? Position. That's the second what? Example. Or you have this. You can also use this. This is the ball. Okay. Slightly displays it, just a little, to move down to what? To the center. To what? To relax. That's to settle. Okay? The next one is what? Unstable equilibrium. Okay? We have this. And we have what? Object. At where? At the top of the what? The circular what? Ring. You can say this is horizontal what? Horizontal ground. This is horizontal ground. That's the ground level. When this ball is what? Slightly or gently displayed, it tends to what? To move far away from its initial position. Far away. It tends to move far away from its initial position. That is, when slightly, that is unstable equilibrium, when slightly displayed, it tends to move far away. Forward away from its initial position. Okay? It tends to want to move away from this position. Tends to move away when slightly on display. It will tend to want to move away from this position. Okay? Such object or such body is in what? In unstable equilibrium. Example 1. When you have coal sitting on his what? Vertex, or sitting with his vertex. This is vertex of cone V. This is unstable. It's not stable. It's not stable. The cone sitting on the vertex. Or the second one, we can have what? A ball. When you have ball, placed at what? The back of the ball. And we have ball placed there. When slightly was displayed, what will happen to the ball? It tends to want to move far away from its initial position. It tends to move far away from the initial position. Okay? Number next, neutral equilibrium. Neutral equilibrium. This is neutral equilibrium. Neutral, that is constant. When a body is what? Displayed, slightly displayed, and the body tends to what? To rest on its what? New position. Okay? Tends to want to rest or relax on its what? New position. Different from unstable. Unstable will far away from it, while what? Stable will remain there. Okay? Example of that is this. Example is this. That's the first example. This is the word pipe. Okay? When you was display this word slightly, it will tend to want to relax or to rest on its what? New position. Likewise, this also. If you display this marker that I'm holding, okay, let's assume that the marker is what? Facing this side, and you try to what? Displace it a little. There's probability of this not what? Coming back to this. Okay? Can try to what? To relax here. That is neutral. Okay? Or like this. That is neutral. Okay? Not this position. That's neutral equilibrium. And the second one is what? When you have coal resting on his what? On his slant length. On his slant height or side. On its side. This is what another example of neutral equilibrium. Don't forget the diagram. You can always differentiate between what? Neutral and stable, unstable, and neutral equilibrium using the what? The diagram given. Very, very important. Okay? So let's look at another subtopic, which I called what? Moment. What we mean by moment? Moment of force is the product of the force and its perpendicular distance in the direction of the force. Okay? Let's say for instance that we have this. Okay? We call this to be A, we call this to be B. If we have this to be, we call this to be F1. Okay? Alright. Under. We call this to be what? The pivot. Okay, that's the support. Or you call it knife edge. That's the support. So the distance from there to here, let's call this to be x1, and the distance from this end to this end, we call it to be f2. So we can have this to be s2. Okay, let's call this to be s2. Okay, moment is what? You can say what? Moment equals to the product of force and its perpendicular distance, that is f1 times x1, that is equals to f1 x1, okay, and also f2 times what? Times x2 times x2, that will give you what? f2 x2. So this is the moment of this force. Why this is also what? The moment of this. So these are the two what? The moments, which is the product of force and its perpendicular distance in the direction of the force. The perpendicular distance in the direction of the force. The perpendicular what? Distance in the direction of the force. Now let's look at what? Principle of movement. Principle of movement. The principle states that some of the clockwise forces in one direction must be equal to some of the anti-clockwise forces in another direction. That is just the principle. That is, the sum of the forces acting in one direction must be equal to some of the what? Anti-clockwise. When you say what? Clockwise, the way your what? Your normal what? Wall clock rotates. That is clockwise. The way your what? Your normal wall clock, the way it rotates. That's what? Clockwise. That's clockwise. But I've never seen that before. When you see clock rotating backward, I've never seen it before. Okay, but if possible, that is what we call what? Counterclockwise. Counterclockwise, or you call it anti-clockwise. Anti-clockwise. That is on principle of what? Of movement. Okay, let's have this diagram. Oh wow, bad. Alright, this is okay. So let's call this to be A. We call this to be B. Okay, let's call this to be the center. The center, okay? So we have this to be F1. We have this to be F2. This is F3. Why this is F1? F4, right? Okay, let's see the distance from here. From this point to here is x centimeter, and let's call this to be what? Let's call this to be x1, x2. So the distance from here, okay, from here down here, let's call this to be x3. Y from here to here, we call that to be what? To be x4, right? Of course. Where's the moment? What will be the moment of this force? We said what? The sum of the clockwise moment must be equal to what? To the sum of what? The anti-clockwise moment. That is what principle of moment states. So when you have this now, this will be what? This will be anti-clockwise. Anti-clockwise, moving backward. You can see backward. So also this also anti-clockwise. This will be clockwise moment. So anti-clockwise moment, anti-clockwise moment. This is also what? Clockwise moment. Counterclockwise, clockwise. So from here, we can deduce that, okay, the sum of the clockwise moment, sum of the anti-clockwise moment, what will be the sum of the anti-clockwise moment? When you say sum means what? Plus. So we can have F1, okay, let's do this way, equals to F1, the distance of this force from the pivots, okay, from this support, that will be times x1 plus, we say sum. Sum talks about what? Addition, okay, plus we have f2 times what? Times x2, okay. That's for what? For the counterclockwise moment. What about what? Sum of clockwise moment. That will be what? F3. Okay, let's say F4 times what? X4 plus what would this be? This will be F3. F what? F3 times X3. Okay, since principle of moment states that what? The two must be equal. That's the principle. So therefore we can say that what? F1x1 plus what? F2x2 must be equals to F4x4 plus what? Plus F3x3. Okay, that is what? The principle of what? Of moment. Okay, let's quickly look at what? Couples. C-O-U-P-L-E. So what do you mean couple? When you have two parallel forces acting in different different direction. Two parallel equal forces. Yes, I love that. Parallel but equal forces acting in different direction. Let's say for instance you have something like this. The example of couple is your what? Your tab. Your tab. Something like this. I'm not good at drawing, but something like this. We have two forces, right? Okay. Then make it more what? Good. Okay, something like this. Your water tap. You know, taking a what? A T shape. Okay? We have two what? This is what we call what? Two parallel but equal forces acting in what? In different direction, not in the same direction. So this will be F1, this is F2. So this is an example of what? Couple. Okay? So this diagram can be what? Be summarized here. We have this, that's the distance apart. So we call this to be half. Alright. This will be the what? The vertical force. Let's call this to be F1. This will be F2. That's F2. Can you see that? They are equal. The two parallel forces acting in what? Different direction. They are equal. Meaning that what? F1 is equals to what? Equals to F2. F1 equals to F2. F1 equals to F2. So we can say what? Couple, take for instance now, if you have this will be 4 Newton. Okay? And we have this also. Since they are parallel, they are equal, right? So this will be 4 Newton. Are we together? Parallel but equal forces. So F Newton, 4 Newton, 4 Newton. So, and at a distance of what? Let's say at the distance of, okay, let's say at the distance of 2 meters. At the distance of what? Of 2 meters. So we can say what? Couple equals to F times R. F times R. F times R. We're picking one for because the two forces are what? Are the same. So this will be equals to what? FR. Okay, relating this now to the what? To the formula, to the question. So R is formula, F is what? Is 4 Newton. So therefore we can say couple equals to 4 times 2, and that gives what? 8 what? 8 Newton. Because we are talking about what? Force. Okay, in what? In Newton. In Newton. Let me also back it up with this diagram. I love drawing. Let me also back it up with this diagram. With this beautiful diagram. Okay? Look at this. We have a meter rule. A meter rule. A meter rule. What is this? Okay? Let's manage this. Meter rule F. Let's call this to be F1. Okay? Coming up on again. Down there. Then we have this. Alright, so we can have this will be F2. So this will be what? Perpendicular. When you say perpendicular, that is at angle 90 degrees. We call this point to be A, this point to be what? To be B. Okay? So the moment will be what? This is what? The couple of two parallel forces acting not in the same direction, in different direction. That's what we call it what? Two parallel but equal forces. Can you see that? Two parallel but equal. They are equal. Okay? This is another example. Okay, let's move further to what? To center of what? Center of gravity. Center of gravity. How we can locate center of gravity? Center of gravity. How we locate the center of gravity? So let's say for instance that we are in cone. This is cone. Cone. We have this like this. Okay? This is the base of the cone. And of course we know that from this point to this point is what we call what? The height of the cone. Yes or no? Yes. Height of the cone. Okay? Height of the cone. Normally, the center of gravity, meaning that what? Where the what? The weight, okay? Or the sum of the forces acting on that body is what? Felt or act. That's what we call center of what? Center of gravity, okay? so we can take, okay, that, let's take for instance that the center of gravity or the weight on this one, on this of this cone is at where? At the center, that is W. That's what, where the weight of what? Of the cone is what? Is felt. That's the center of gravity, okay? So from here we can deduce this. Since this is half of it, so this will be 1/2h. And now from here to here will be 1/2h from this point to this point. So we can have from this point down to this point, we give you 1/2h. From this point down to this point, we have 1/2h. So addition of the two must give you that. Okay? Adding this and this together must give you this. This is for what? For a cone. Okay? What about if you have something like this, something like this, something like this, something like this? We have what? A meter rule. A meter rule. You know, normally a meter rule, the length of a meter rule is 100 centimeter. Is 100 centimeter. So if the length of a meter rule is 100 centimeter, we know that what? The weight of the meter rule will be at the what? The center. That center of gravity. Where the what? The weight of this is what? Where the weight of this acts. Okay? That will be the center. So from there we can say what? If we got this to be L, if this is L, alright? And this is what? The center. That will be the one, the weight of the meter rule. So we can have L by 2, L by 2. So L by 2 will give you what? The center. We can also have what? When we have a what? A circle, alright? We can locate the center by what? By just drawing a what? A straight line from this end. Oh, sorry. Not really straight, okay? Let's draw right. This is manageable. We have this also. Okay? Draw a perpendicular line intersecting at this point. At this point, where the weight of the what? The circle will be. Okay? That will be the what? The center of what? Of gravity of that circle. Thank you and God bless you.